Hello and welcome back, everybody. So we've reviewed some complex numbers and the trigonometric form of a complex number. Now we're going to talk about the exponential form of a complex number, and this is where things get a little weird in pre-calculus. This is where we start talking about complex exponents and what does it mean to raise a number to like an imaginary number or a non-real number. Okay, we kind of know how to deal with it when we're raising numbers to, something like 5, right? We're just multiplying it by itself 5 times, or raising it to the negative 5 power. That would just be the reciprocal of that number to the 5th power. But what happens when we raise it to like I? And this is kind of weird. So this brings us to Euler's theorem, which says that e to the I theta is equal to the cosine of theta plus I sine of theta. Now, this can almost be taken like as a definition of what it means to raise e to a non-real number, or some number times I. There is a proof to this. For those of you who take Calculus 2, you will see how this is kind of proven using power series. Right now, you might as well just take this as gospel. Take this maybe as a definition. Okay, it's just cosine theta plus I sine theta, and we can generalize this. We can multiply both sides by r, and we've got re to the I theta. It will be r times cosine theta plus I sine theta. And the expression on the left is, or rather on the right, is a lot more, is basically the trigonometric form of a complex number. But I guess we're out this. This is the trigonometric. I guess maybe I should say that this expression, we call that the exponential form of a complex number using just e. So the important thing is it's still all about r and theta. We just rather than write this all out, we just use this with this e notation. Using this convention that e to the I theta is this. Okay, so for example, from last time we looked at 1 plus I. R was the square root of 2, and theta was pi over 4, so 1 plus I is square root of 2 times e to the pi over 4 times I. Negative I is now, we said the theta from last time, we said theta was 3 pi over 2, and R was 1, so minus I can be written this way. 2 plus 5i can be written this way, as we said that from the last time we found that r was the square root of 29, and the angle theta was the inverse tangent of 5 halves. So this would be the exponential form of this number. This number is just a little more something we know. E to the 2/3 I. The reason for that, of course, is that this is the cosine of 2/3, the 2/3 pi is this, and the sine of 2/3 pi is this, square root of 3 over 2, right? So that's why e to the 2 pi over 3 times I is equal to this number. Interestingly, e squared, well, it's exactly what you would think it would be. E squared is e squared times 1. And so e squared is 1 can be written as 1 plus I times 0. So that's 1 is cosine of 0. 0 is the sine of 0. So here we have e squared times e to the 2i. So the trig form could be e squared can be written as e to the 2 times e to the 0i, or you can just write this as e to the 2 plus 0i. When you get into higher math classes, you're going to see that the power, all the exponential rules for real exponents carry over to complex exponents. So you'll see this if you take a course on complex numbers or complex variables. Here, a very interesting thing here, a famous equation is that e to the pi I is equal to -1. Some of the people say that is Euler's biggest contribution, because here's a simple equation that relates the three mysterious numbers e, pi, and I all together in the same equation. And this is, pi I is the same as I times pi, and this is really just cosine of pi plus I times the sine of pi. So it's -1 plus 0, which is just -1. Okay, so that's the consequence of Euler's theorem. Another thing here is that the advantage of working with complex numbers in their trig form or exponential form is that multiplication is pretty easy now, or easier. Because if for example, if z1 and z2 are complex numbers, and these are their exponential forms, and we want to multiply these two numbers, we can just multiply their respective r's and add their respective thetas, and we get this number. Now this, it seems like it should follow, right, just from the rules of exponents, but we haven't really proven the rules for exponents, for complex exponents. Okay, so I want to just show you let's say, assuming you didn't know that these rules work for complex exponents, we can still prove this. And no, this won't be on the test, but just so you know where this comes from, why this works. So we can put this in the z1 and z2 in their trig form, and then group the r's together, and then put these two expressions together. We can FOIL these out, and we do that, we get cosine of theta 1 times cosine theta 2, and then the last term would be I sine theta 1 times I sine theta 2. Well, I times I is I squared, which is -1, so that's where this minus sign comes from. So we got minus sine theta 1, minus sine theta 2. So these two terms together are the real term, and then the I terms would be, or the imaginary terms would be sine theta 1 times cosine theta 2 plus cosine theta 1 sine theta 2, which is how we get this expression. And then this is where our awful summation and difference formulas help us out. This expression is just the cosine of theta 1 plus theta 2, and this is the sine of theta 1 plus theta 2. We didn't think we were going to use this again, but we are, and so it helps out a lot. And then this is just r1, r2 times e. By how we define this is just r1, r2 times e to the theta 1 plus theta 2 I. And as a special consequence of this, if theta 1, if z1 and z2 are the same, let's say they're both equal to z, and if theta 1 and theta 2 are equal, and they're equal to theta, and the r1 and r2 are equal, they're equal to r, then z squared will just be r squared e to the 2 theta times I, which is really just r squared times cosine of 2 theta plus I sine of 2 theta. Okay, and then we can do this we can also compute z cubed the same way. Z cubed is of course z times z squared. This is z squared. We just computed. We can group the r's together and get r cubed, and then multiply this mess out. And then once again, by the sum and difference formulas, this is just the cosine of 3 theta, and this is the I plus I times the sine of 3 theta. And hopefully you can find what the pattern is now, is De Moivre's theorem. De Moivre's theorem was a French mathematician, and you can probably guess. Well, he proved the following: if n is a positive integer and z is a complex number in this form, then z to the n is just r to the n times e to the I n theta, or in trig form it's cosine of n, r to the n times cosine of n theta plus I times sine of n theta. So that's kind of helps us out some, okay? And it also shows that the angle is not just changing. If we take an angle, if we take a complex number in the plane, okay, and if we just if we take an angle, a number on the real axis, if we keep multiplying it, if we could take squaring it and cubing it, we just get bigger and bigger numbers, right? But they're all on the x-axis because theta is 0. But then if we take a number that's off the x-axis, like here, the real axis, the modulus is going to keep going, and the powers are going to get increasingly further from the origin, but they're also going to be at have different arguments. So let's see how we can do this. If we want to compute 1 plus I to the 13th power, okay, so we already know that r is the square root of 2 and theta is pi over 4. So this should be equal to square root of 2 to the 13th power times e to the I times 13 pi over 4. Okay. Now this simplifies to the square root. This is 64 times the square root of 2. That's what this is, and then this will be the cosine of 13 pi over 4 plus I sine of 13 pi over 4. Okay. But what is this? Well, 13 pi over 4, this is the same thing as the cosine of, if we subtract 8 pi over 4, 8 pi over 4 is 2 pi, so we can do that because the cosine and sine have period of 2 pi. So subtract 8 pi over 4, you get 5 pi over 4 here. Okay. 5 pi over 4 is in the middle of the third quadrant, so this is actually going to be negative root 2 over 2. Yeah, this is negative root 2 over 2. Okay. So this is going to be 64 times the square root of 2 times root 2, negative root 2 over 2, plus I, maybe I'll just make this minus I sine root 2 over 2. Okay? And this actually turns out to be negative 64 minus 64i, because this square root of 2 times square root of 2 is 2, 2 divided by 2 is 1, so this will be negative 1. 64 times negative 1 is negative 64. Similarly, we get this. Okay. So we were able to do that out. We didn't have to use the binomial theorem or multiply this out to do 12 different calculations. So that's kind of nice. Let's do one for, in this example, square root 3 minus I raised to the 8th power. And in this case, we can choose to see that r is going to be 2, and theta, we said, is 11 pi over 6. I think we did this on the previous video. Okay. 11 pi over 6. Now, we could all, at this point, it's going to be a little easier just to write this as negative pi over 6. But let's keep 11 pi over 6 here. And so this is going to be 2 to the 8th power times the cosine of, okay, so we're multiplying 8 times 11, so this will be 88 pi over 6 plus I times the sine of 88 pi over 6. Okay. And then this actually is going to be, you can actually reduce this by, subtract multiples of 2 pi, and this is going to actually be equal to the cosine of 2 pi over 3 I think. And this is going to be equal to the sine of 2 pi over 3. The reason for that is 2 pi over 3 is the same thing as 4 pi over 6. And you can, so the difference between 88 and 4 is a multiple of 12. So you subtract 2 pi here, but you're really subtracting 12 pi over 6. So keep subtracting 12, multiples of 12 from 88, and eventually you get 4. Okay, so 4 pi over 6, which is 2 pi over 3. So this is going to be 2 to the 8th times negative 1/2 plus I times square root 3 over 2. And when you simplify this, this is going to be 2 to the 7th times negative 1 plus square root 3. Sorry about that. Maybe if we want to do one more, here 5 plus 2i to the 6th power. We already found out that r is the square root of 29, and theta is going to be the inverse tangent of 5 over 2. Okay, so we can just do this. So this is equal to square root of 29 to the 6th power times the cosine, well, times e to the 6 times the inverse tangent of 5 over 2i. So this is going to be the square root of 29 to the 6th power cosine of 6 times the inverse tangent of 3/2, or rather 5/2, plus I times the sine of 6 times inverse tangent of 5/2. There we go. Okay, now, if you do this right in your calculator, you do get some a very nice number. If you just take this number and round it to 3 decimal places, you're not going to get this nice answer that I'm going to write down. But if you actually compute this in your calculator and take, like cosine, of 6 times the inverse tangent of 5/2, okay, and then go from there, then this does work out. And what this current works out to is this is equal to 15939 plus 18460 times I, okay, if you wanted to do that. And you kind of know that that your answer should be some integer plus another integer times I, because of this. Okay, if you were to multiply this out by brute force, it would be kind of ugly, but you would know you're just multiplying integers and adding integers together. So you should get a nice integer like this. And you will get this on your calculator if you do it. If you actually use this as your value and not round this to 3 or 4 digits and then try to plug it in. Okay, because then you get problems. All right. Okay, so that's De Moivre's theorem. That's how to compute powers. And then in the next video, we're going to actually try to find nth roots of complex numbers. So we'll see you in the next video.